Anyway, to get things started off today, we're going to be getting a talk on the heart of what makes routers route these days, the ASIC, from Chang-Hong of Juniper Networks. Whoops. 9:45. You're right. Oh, 10 minutes early. Yeah, sort of surprised him a little bit. My announcements didn't last 15 minutes. I don't know why when we put together the agenda we thought I was going to talk for 15 minutes. I could do that, but I don't want to bore you to tears. So we're actually going to get started a little early. Somehow I have a feeling we'll manage to lose it all before we get to lunchtime anyway.
Right, let me get the slides up somehow. This works, right? And that. Yes. Everything's good. And good morning. It's nice to be here today. So I designed ASICs, and it is not usual that we come out and talk to this many people. So in a corporate hierarchy, we are usually hiding behind all the sales, support, software, and hardware. Then we are the inside of the routers. So I really appreciate the NANOC program committee that giving me this opportunity to share our work today. So hopefully through this, you get some understanding of how we design the heart of the routers, and then we can also, through some dialogue, and serve as a catalyst so that we can better serve your needs in the future. So everybody, all of us are aware of the exponential growth of the internet over the last like 10, 15 years. No matter how you measure it, on this graph there shows a lot of measurements that people take. The internet is taking an exponential path for growth, no matter how you measure it. This doesn't come about by itself. Of course, we are delivering value to our end customer. That's why it grows. Fundamentally, what is the driving force behind all this exponential growth? The way we see it are the interaction of the computing and the networking and the storage elements inside an information system. Right, so by themselves, the computing and networking and storage all grow by themselves over time, but it is the interaction and the ability we connect them together that make this information system more valuable to our customers. And that's what is driving the growth. And more valuable the total package, and it also makes the individual components grow faster. And it's this positive feedback that drive the exponential growth. That is driving force, but what is behind this exponential growth in the last several decades are the improvements in silicon integrated circuits. And here on this diagram, we are showing the performance improvement of a computer system in the last 20 years or so. You can see the system itself is growing almost like 2 times a year. And the microprocessor itself is growing at about 1.5 times a year, 1.3. And you can see the system itself is growing faster than the individual components, and that shows the value of the interconnect. Right? And even inside a computer system, there is a network, or some sort of interconnect that connects the components together. And more relevant to this talk, we are showing the router performance improvement in the last 20 years. And we are showing there are 2 phases in this development of the routers. And one is before the middle to late 90s, That's before the ASICs are widely used in routers, and the improvement of the routers are only 1.6 times a year. And this is roughly consistent with what computer system will give you. And that's not surprising, because at those days, the routers are made from computer systems. Right? But after the ASICs become widely used in computer systems, in routing systems, the pace of improvement has increased dramatically. And as you can see here are several examples of what Juniper systems delivers. And I'm sure this is true in general as a whole. And in the post-ASIC era, the router systems are improved at a rate of about 2.2 times a year. I mean, the 2.2 against 1.6 probably is not a big number to start with, but if you do that year after year, and this will make it into a very big number, you can see there's a million times of growth of router performance in 20 years. In a large part of it is because of the use of ASICs in the later part of that 10 years, of the 20 years. So we can see the role of the ASICs in the router performance improvement. And now we take a look at how we categorize the use of silicon inside a communication system. And then we classify them based on how much information they process. So here the instruction is a kind of an abstract measure of how much the system treats the packets or the information. And from the left, which has less processing per packet, and all the way to the right, there's more processing per packet. We classify them as a fabric engine, and core engine, and edge engine, and service engine. ASICs play an important role in almost all of these categories. And each ASIC system does not have to play in only one of these categories. It can play in multiple of these categories. In fact, most of the innovation are driven off that. One can give advantages in several different categories. And here's another way to look at the comparison. I talked about ASICs. I never explained what that means. ASIC is an acronym that stands for Application-Specific Integrated Circuit. By its meaning, by its definition, it's specifically designed for your task. So here are the few types of devices we use in building routers or communication system in general. And they all have their advantages and disadvantages. And for the right usage case, they could be the right answer. The first one we look at in this table is the general purpose CPUs. And these are widely available. The advantage of them, of course, is they are very flexible because they are programmable devices. They can do anything you want. But the disadvantages in routing systems are they are not as good in performance, density, and power. And the case that it is the right answer are in cases where flexibility is more important than performance. And most of the cases are the low-end routers. And we see them a lot even in commercial systems. And then the next one down, we call them field programmable gate arrays, or FPGAs. And these are devices that is already built, but you can program them at runtime to do the logic function that you designed. And the advantages, of course, they are compared with ASICs, which I will talk about a little bit later. They are smaller upfront development costs because these devices are already there. And also they are upgradable on the field after you develop it. And the disadvantages, of course, is they are lower performance and density and power than ASICs, and they are also higher per part cost. And the cases these are useful, and probably even advantageous are when the volume is low because the price is high, and when changes are expected. So, for example, if one of the standard that you are designed to is not finalized, and you can use this, so you can upgrade them when the standard is finalized. It's very useful. And the third category we categorize them in is the network processor. These are flexible devices, and they are already made. You can jump straight into software design. So that's the advantages. But sometimes they are not specifically designed for your task. You have to compromise their performance, power, and functionality targets. But of course, there are useful situations as well. When the hardware differentiation is not that important, then you can differentiate with software. But of course, I mean, depends on how they are designed. There are some features you may or may not be able to deliver with the devices already there. In the last one, we can see those are the ASIC, the application-specific integrated circuits. And they are tailored exactly to your specification. That's the advantage. They are high performance and comparably low production costs. But the disadvantages are also there. They have high upfront cost. In a minute, I will show you we need to pay a very high called NRE cost, or non-recurring engineering costs when we develop these devices, and they also have very long development cycles. But they are high performance, and they have low performance costs, and you cannot escape from them if you design high performance routers. Now we can see, I've talked about the roles of the ASICs play in routers. Now I will turn my attention to see how we design them. And we start with system architecture. At first, of course, anything that we design need to meet the market requirements in performance, density, and feature and cost. And then we look at it from a lot of angles. One is software hardware partitioning, and how much of the function are done by hardware and how much of them is done by software, or how much of them is done by both interacting with each other. In fact, most of the things we do are the interaction between software and hardware in the router systems. And we do silicon fabrication process technology evaluations. And I have another slide, talk about more details, but that's the cost-performance trade-off we do. And a very important aspect of designing ASICs in routers are the choice of memories. And we use memory for working buffers, delay bandwidth buffers, congestion management, and also the store configurations and the forwarding tables and the access control list and all of that. And the choice of routers plays a very important role in determining your feature and the cost of this finished system. And then we also look at chip partitioning, and we have to make sure the partitioning makes sense in terms of feature, performance, and cost targets. The first aspect, the fabrication technologies. And one thing about silicon process is like they improve over time remarkably. And then the greater density of these processes can put more gates on the same device area, which will give you more function in general. And there's a Moore's law that has been existing for quite a while, and which was proposed by Intel's founder, Gordon Moore. The transistor density doubles every 18 months. And people have been talking about the depth of that law for a long time, but remarkably, it has been holding up very, very well. It is still going pretty strong. But how long can it last? We don't know, and we don't know when it will not get that scaling. But thankfully, we are still there. So we should be thankful. But before, like 5 or 10 years ago, The scaling of this semiconductor process technology give you advantages not only in density, but in power, in performance, in everything. But this has recently changed in the last 5 years or so. The silicon process technology, the density is increasing, but the performance is starting to level off. And also the decrease in operation voltage, which comes every generation, has also slowed down quite a bit. The reason for that is that we are reaching close to the fundamental limit of the semiconductor, how semiconductor works. So because of that, the performance also, like I said, has slowed down. Well, the performance did not slow down, but the improvement of performance slows down. And also the other side of it is the dynamic power, because the voltage are not dropping as fast as we would like, the dynamic power reduction had also slowed. And on the other hand, the static power, mainly due to leakage, had increased dramatically in the last few years, and which is very, very important to our system, is the power. So because of that, we cannot rely on the fabrication technology improvement itself to do our designs anymore. There are a lot of architectural innovations needed to be there to deliver value to you. And there's another bullet point there that says NRE cost. That's the non-recurring engineering cost, which we pay for every device that we produce, no matter how many we sell. So these ones, the money in NRE is range in millions of dollars per chip. And this has increased on every fabrication process improvement, every step of the way. And you can see on this diagram on the right side, those are the cross-section of a silicon device, mostly the vias that connects between the layers. And those rectangular thing are actually cross-section of a wire on the device. Now let's talk about memories. On this diagram, we are showing a system of ASICs, although I draw one box, but they could be multiple ASICs, and they are connected to a bunch of memories. Of course, one side of it, you have the input of the packet, and the other side, output. You can either go to the line, like Ethernet, or optical, or SONET, or any of the ODUs. There are several types of memories we use from the functional perspective. On the top there, one are the packet buffers, and some of them are just temporary working to store there. And another role that plays is to store the packet when there's congestion. And then the packets are usually segmented into fixed size cells, and they need to be linked together. That's the memory I show on the right side of the top. Those are the queues and link memories that you are using it to find the entire packet. So the packets are usually managed as a linked list on our chips. And we have one way or another dealing with it, but fundamentally they are linked lists, and that's what the link memories are used for, to find back the entire packet. And then on the bottom there, those are the control memories, and they are used to store the forwarding tables, the ACLs, access control lists, and all the configuration and etc. that you use to control the routers. Here is a big table that shows the different characteristics of different types of memory technology that currently are available to us. And these are not all of them. There are a few more. So I don't expect you to look at every single one of them and make sense. So here, H means high, M means medium, and L means low. And all of these are relative. So I would like to highlight several points. The embedded memories on the first 3 rows are the ones that are residing on the ASIC themselves. And the external ones are outside of the ASIC on the board as a separate components. And in general, anything that's on die, the embedded ones, have higher frequency, which is translates to performance, and lower latency. I'll explain in a minute why that's important, and burns less power operating them. But they are smaller in capacity, and for the same size, they will be more expensive than the external counterparts. But of course, they are smaller size. If you just want a smaller size, they could be less cost to design if all your requirement can be satisfied with on-chip memories. And the external memories, of course, the exact opposite of the on-chip ones. They are higher capacity, but they are lower performance, lower latency, and power. But between different types of memories, we can see there, and they are also different. The SRAMs, which stands for static RAM. These are 6 transistor cell devices for each bit. And they are higher performance, lower latency, but they are smaller and more power hungry than the DRAMs, which stand for dynamic memories. And the dynamic memories are the ones that you usually find on PCs. Those are the ones that have high capacity, but they are not as high performance. Also, they have higher latency. But the big advantage of them, especially for the external one, are the low costs because they are universally available. And there's also another one I highlighted here, are the TCAMs. Those are the ternary content addressable memories. And the normal memory, you give in an address, you read out the data. The TCAMs are exactly opposite of that. You give them a content, they will show you, they will come back with which entry it matches that content. So TCAM has been used in networking for a long time. It's very variable to do ACLs and the like, and even lookup. The advantage of them is that they are exact predictable latency. No matter how big the table is, you send them a content, they will return the address in the exact same time. But the disadvantage of them is that they are smaller, and they have lower performance, and they have much, much higher power. And because there are not many vendors are doing that, and they are also very high cost. So as you can see, there's a lot of choices available to us when we're trying to design a particular feature. So if the memories are smaller, if you design to hold a fifth table, for example, the forwarding table, it will not give you as many entries. The scaling will be limited. And also, if you are trying to implement them on an on-chip memory, you also may face the same problem. So the scalability, the feature, and the cost at the end is very, very much influenced by how we put this memory in use. Also, the one thing that these memories are also silicon devices. They follow the Moore's law too. And so they are changing with time also rapidly. So at each point in time, we have to look at all the available technology to us at that time and see what is the most appropriate to use. And I read a few years ago, I think it was 3 years ago, in Nanoc 39 or so, or 37, you guys talk about the fifth table scaling. And there's a lot of talk about memories as well in there. And just this few years, it's not very long, but a lot of things have changed. Like, for example, in that talk, talk about a lot of SRAM. But since the microprocessor vendors decide to put the level 2 cache on their die, which are most of the high-performance SRAM were used at those days, the market is disappearing pretty fast. In fact, the improvement in the last few years in SRAMs are almost non-existent. So we have to predict, and we have to look at in a few years, because all of this ASIC development takes a few years to materialize. We have to predict in a few years what's available and what is the right cost target and feature target we use, and to decide which one to pick. So here, again, are the three types of the memory that I showed in the previous diagram, and a few of the, give you a few examples of how that is done. One is the packet buffers. For high performance packet buffers, you need high throughput and high density because on the wide area routers, for congestion management purpose, we need hundreds of milliseconds of buffers. And that usually translates to external memories. And then that's why we use SDRAM, external SDRAM for those most of the time. And sometimes because SDRAM performance is not up to par, we use a little bit higher performance at that time, the IL DRAM for that purpose. And the reason we can use DRAM for that is that the packets are usually pretty long, so long bursts are okay. On the other hand, for the queue and link memories, they also need high performance, high throughput, but they need low latency because you need to get the next link before you can get the next. Right? So it's a pointer chasing exercise. So they need a lower latency and a shorter burst. So we need some of the example we can use are SRAM because they are lower latency, but it may not be a good choice because their size is limited. So we do a lot of tricks to use DRAM for this link memory. But you can see that characteristics are slightly different. And the third category is the control memory. And here, for high-performance router, we still need high performance and low latency. But these are small quantums because they are control information. We need them a little bit at a time. So for that, the SRAM and TCAM and RL DRAMs are a better choice than SDRAMs for that purpose. And I'll give some specific example of how Juniper ASICs use these a little bit later. And the last topic of the architecture phase is the chip partitioning. How many chips do we need on a forwarding engine? The notion that I would like to raise here is that fewer chips does not necessarily mean overall lower cost. That's because the chips gets very expensive when the die gets big. And every generation it's slightly different, but if the die gets big, the defect density goes up, and then if you have a bigger die, then you may not get any yield or good chips from that. And that's why the cost increase exponentially once your chip grows beyond a certain size. So we have to keep in mind how many chips, if you look at the diagram on the right, there is a crossover point of whether one chip is the best when the number of transistors is not humongous, but when the number of total transistors required to accomplish the logic increase beyond a certain point, the chip cost will dominate, and also the power you use to cool them may dominate. So you design multiple chips might be more advantageous as a total system solution to split the chips into different ASICs. So the goal is to have the overall system cost instead of just the chip cost itself. And again, even the chip cost itself might dictate you to split them because of the yield issue. And also there's usually the ASICs use the periphery as the input and outputs. And there's only that many peripheral area that's available on the die compared to things on chip. So we have to balance the chips based on their input, output, and the logic you do ratio on the in the system. And we also need to be aware of when you split the chips, you increase the complexity. So you need to be careful to have a clean interface between them. So So these are all the different factors like affecting the chip partitioning in the architectural phase. So as promised, here are some examples that Juniper devices use as to the silicon process, chip partitioning, and memory usage. On the left, which we released in 1998, those are called Internet Processor 1 and 2, and those are used in M40, I believe, and the lower platforms. They are fabricated using 250 nanometer process, and there are 4 chips in each chipset. And the reason we split those 4 chips are mainly due to system partitioning. And the memory we use, for the control memory, we use SRAMs at that time, 125 megahertz only, and use SDRAMs. Those are the single data rate SDRAM, 125 megahertz as well. So those are a long time ago. And then we did a Internet Process 3 in a release in about 2002, and those are fabricated using 180 nanometer process. And, well, in the parentheses, the 90 I'll talk about later. And in this system, there are 10 chips per PFE. And these are 20 gig PFEs. And the main reason to split the chips in that case was memory bandwidth. And of all those 10 chips, 5 of these chips are interfaced to memories, data memories, and queuing memories. And then in that case, we used SRAM as a control memory again, and we caught up in the RAM bus thing, so we used RAM bus as the data memory at that time. And that's the only time we use RAM bus memory. And later on, we extend this one to, so the original chip was designed for T640, and we doubled it performance to T1600. And then we did that chipset in 90 nanometer. And that was a 9-chip complex. One of the interface chip, we combined them together because we were like 2 generations ahead. At that time, we still used SRAM as a control memory. And we switched to RLDRAM, the reduced latency DRAM, as the packet memory. And because we look at DDR SDRAM at that time, it wasn't mature to the point that the performance is not up to par. So at that time, RLDRAM is the best we use. The funny thing about the SRAM also is like we designed the T16 version of it. Right in the middle of the project, that SRAM actually disappeared from our vendor's roadmap. So we have to improvise. So you can see, so with all the planning you can do, there's always some catch there. So later on, in 2006, we released the iChip, which is a 1-chip 10 gig PFE, and that was also designed using a 90 nanometer process. And at that time, we switched to RLDRAM as our control, the reduced latency DRAM as our control memory, mainly because we are foreseeing the SRAM, as I talked before, the SRAM improvement SRAM kind of slowed down. And also RLDRAM will give us much better size because it's a DRAM, so we can provide more scalability to you guys. And then for packet memory, we use DDR2 as DRAM. And then last year, we released a new chipset called Trio, also sometimes called NISP, Network Instruction Set Processor. We designed it using 65 nanometer process, which is an improvement over 90, the next generation. Well, actually, 2 of the chips are used 65, 2 of the chips use 90. And you can see the number of transistors also increased dramatically, so that's the power of the Moore's law. And in this case, we kept RLDRAM as a control and DDR3 as DRAM, and the next generation of memory for our data process, the data packets. So why are we changing all of these from time to time, right? So, of course, is to provide value to our customers. And you can see these are not the same system, so don't look at the same column as before. So they don't correspond to the previous page. But anyway, with time, from 1998 to 2007, we have 4 generations of core routers. And then, because of the improvement in silicon technology, and of course a lot of other things as well, and all the system capacity, slot capacity improved while we decrease power per bandwidth, or we increase the per power bandwidth we delivered. So from 13 gigabits per kilowatts to 96 gigabits per kilowatts in a 10-year span. So that's the power of ASIC improvements. Now we are done with architecture phase. Now it's time to sit down and do the design ourselves, right? So we decide the chip partitioning, we decide the memory we to use, we decide everything. And now people, human beings, design things by divide and conquer, because that's the only way we know. We don't know how to deal with too complex a thing. So we divided the system to its individual chips, and now we divide the chips into subsystems, and subsystem into blocks, into subblocks, and then all the way down to the basic logic elements. And in this phase, we document these functionalities, and the main criteria we use are peer reviews. And with some of the modeling we're also using to model the microarchitecture. As you can see on the diagram on the right, you split the chip into input and output. And input, there are 2 functions, and one of the functions have both control and data path. You design them separately and see what the logic is inside each. And then we translate the microarchitecture into register transfer level language, or we call RTL. So on the diagram, you imagine a logic element and you translate into something on the right. There are 2 ways of coding them. One is on the top, the other one is the bottom. The top one probably doesn't look like C that much, and the bottom one, the assign out equal to select, looks exactly like C, right? So, yeah, these are we spend the most time doing this. These are the functional designs, and we translate everything into this RTL code. And then a large chip will have hundreds of thousands of lines of these. And I think that statistic might be a little old, but yeah, that's the order of magnitude. And also the other thing is that although they look like C, they are not software. They will get translated into hardware. They will have devices corresponding to them. So that's something that we need to keep in mind when we write these C-like RTL codes. If you don't do that, because things are spread out and you take a lot of gates and the performance will go down, you will have to modify your design. So for example, one very different example, a prominent example compared with C and the hardware are like shift registers are very cheap in hardware because you just wire them differently. There's no logic involved, right? So, but a shift, a barrel shifter, it's easy in software. It's not that easy in hardware because it's a multiplex of many bits. So that's one example I would like to give. So keep in mind, those are hardware constructs, although they look like C. And this is the step. We move the RTLs, the register transfer languages, into gates. And if you want to use the equivalent of the C, these are the machine languages. What we usually use synthesis tools to use the inputs into the synthesis tools are the RTL code and the specification of what clock frequency you need. And also what kind of wiring that you expect it to be. And then the tool will translate this RTL into physical gates, like physical logic elements. You can may or may not be able to see on the right side of the diagram are flip-flops. I can see them. XORs, exclusive ORs, inverters, and also those AND or invert gates that you learn in college. So this is a very important step. This is the first step that in getting into the logical domain into a physical domain. And the recent trends are because the physical in the lower geometry, in the smaller geometry, the physical effects is actually very, very important. So some of the recent synthesis tools also takes physical placement into account. They are called physical synthesis. While we design these hundreds of thousands of lines of code, how do we know it's correct? And then we do verification on them. And the goal, of course, is to be able to achieve first-time correct silicon. Because ASIC respin will have to pay the NRE, the several $1 million NRE again for each time you respin an ASIC. So we would like to avoid that. And also simulations are a lot easier to debug than real chips. Okay, when you look at the real chips, you cannot see anything. All you can see is that it doesn't work. So simulation, you can actually see the internal value, internal signals and everything. So it's a lot easier to debug when you can see the problems. So the recipe we have is like to provide at least as many verification engineers as design engineers. And in this day, probably there need to be more. And we perform the verifications at multiple levels, at a block level, at a chip level, at a subsystem level, at a system level. And also we perform software and hardware co-simulations so that the software can work together with the hardware before the hardware is available. And the tools we use, there's a lot of, we use C, C++ to do that, and system Verilog. And Verilog, people use that as well. We use coverage tools to make sure that we cover every line of code. And then we use equivalency checkers to check between the gate, the machine languages versus our RTL languages. And then we use simulators, we use waveforms to look at the waveforms so that we can see what's wrong when something doesn't work. And there's also another aspect of it, is after those synthesized into gates, we need to place them physically on the die. And we just don't do that randomly. And we have to, at these days especially, the power and the clock, because the power of these chips are so high and the voltage are so low, the currents are very, very high. So as you know, the currents go through a resistor will cause a voltage drop. And we have to have a very good power and clock network on the chip as well as on the board to make sure these things work. So we perform floor planning to see where the logic should be placed. And then we place all the IOs, the input and output, and all the big SRAMs on die to their specific case. And these are usually done by hand, not by tools, because we understand how the logic flows, how the data flows, and all that. And we place them by hand, and after that, we place we call it random logic, which is synthesized logic, by tools usually. And then we perform congestion analysis before we wire the wires up. And then if it doesn't work, we have to go back. And then after we determine the placement is reasonable enough, we wire them up. And then of course, we run timing every step of the way above. And with the physical placement, we extract the parasitics. Those are called parasitics, and the resistance and the capacitance of the wires, of the physical wires, and run timing simulations with the gates, and to make sure they work to the frequency we desired. And we do many, many, many of the iteration of the above. And in fact, why these ASIC development takes a few years, and this is the main part of it. And RTL, of course, is the other part to make sure functionality is correct. But So here are some examples of physical design. So here are how we place all the memories, all the black things. They are not voids. They are real memories on the die. And the thing on the side are the I/Os, the input-output elements. And then here are all the gates placed. And then we wire them at one layer. Each layer, the metal 1 and metal 2, we usually have multiple level layers, and each layer goes in one direction, and then the next layer will go perpendicular to that. So these are the M1 wiring, metal 1 wiring, and the metal 2 wiring, metal 3 wiring horizontally, metal 4 vertically, metal 5 horizontally again, metal 6 vertically. And that's the old days. I think this chip is probably 6-year-old. Now we're up to metal 10. And here are probably some of the power routing. And you can see how difficult it is to do this. But then, one day, we are done, right? So the criteria, what we call tapeouts, are the one that we say, okay, we verified all the functionality we have done, and we verified them, they all worked to our best of our ability, and performance simulations, and is that okay? That's what we need. We are there. And chip is also error-free from a testability perspective, because these chips are very complex devices, and in manufacturing there are defects, and we need to weed out those ones that are defective. So we have the design testability logic in there to test the chips too. And then chips also mix timing and all the process temperature and voltage conditions. All these silicon devices depends on what is the temperature and everything. They actually have different timing. We have to make sure they work on all conditions. And then we archive all the databases, and then we tape it out. And after we tape it out, the mask house will generate a mask, depends on the design we do. And this is one of the main reasons these are $1 million NREs. These masks are very, very expensive. And then the ASICs are built on a layer-by-layer process from the bottom up to the top. And then that takes a couple of months, I believe. Once the ASICs wafers are complete, and then on the right side there's a wafer, there's a lot of chips on them, and then each die is tested on the wafer themselves and make sure they work. And then when they work, we'll only cut out the working parts and put them in a package. Those are the chips that you will see if you ever buy a CPU, those are the chips. And after they cut, they put it on a die, and they are tested again on the package level. And then we get the chips, and then we put them on the board, and then we test them again with software and hardware. They work. They are designed to work with. And then if we all prove them they work, then we ship them to customers. So here are some of the pictures. On the lower left, that's the fab, and all the people wearing bunny suits in there. On the top left, that's the wafer with multiple chips on them. On the top right, those are again the cross section. I think in this case you're seeing a lot of wires horizontal because you're cutting on the wires themselves. And then on the bottom right, those are the packaging machines. I'm not sure actually. These are probably the wire bond machines we used in the old days. Okay, then we ship the product and we are done. Right, so here are the summary. So ASIC technology, as we can see, we transformed the network industry. We gave the performance boost we desperately need. So the internet is exploding. Well, not exploding as that, but the traffic it grows exponentially. ASIC technology is required for us to reach that performance level that we are to deliver. And silicon process technology is evolving at a very impressive pace and more slow. But architectural innovations are still required to keep up with the performance demand. And you can see there, the design and verification process, architectural phase, it's very important and it's very long, it's very rigorous to implement these complex devices. And also there are a large number of trade-offs we make during the architecture and the design phase. And it takes that many years to produce these devices. So we would like you as the user community to give us feedbacks what you are going to see in 5 years, 3 years, 5 years from now, so that we can design a better product for you. Right? So I guess that's it. And we are opening up for questions.
Yeah, we got a few minutes here for questions, if anybody has any, and aren't just sitting here in stunned amazement like I am.
Anton Capella, 5 Nines Data. Excellent presentation. Thank you. I am curious if you could maybe provide some of your experience and comment on what you see as far as maybe the trajectory or in terms of where things are headed, specifically with respect to power budget and allocation of power among, say, componentry of the ASIC you described here with, of course, it has some memory, it has some logic, it has a bunch of glue on it. Where do you see things happening, maybe, say, in the TCAM world and, specialized lookup type ASICs or controller ASICs that use these parts? Where is the power going to be going more or maybe going less as you see things going in the future here?
That's a difficult question to answer. In terms of TCAM, I think the market is condensing pretty fast. Right? Currently, so I see challenges how they will scale to a higher performance without increasing the power more. Well,
I guess to cut to the chase, I guess the question is, do you see us scaling TCAM up against the natural limits of what we can conduct on the various design techniques today, against maybe memory assisted or things like the IP2, IP3, of course, SRAM arranged or DRAM arranged around a smarter or perhaps increasingly partitioned chip. And maybe this is naive, but is the power budget and the I/O capability actually a bounding factor in TCAM design versus other memories plus search ASICs?
So I'm trying to not to talk about specific stuff in the company. It's one reason that actually Juniper does not use TCAM that much is we are shy away from their power. So TCAM is by nature a parallel logic process. So by nature it will burn more power than SRAM memories themselves. So I think even the vendors they are looking at different ways of improving that. So I don't want to speak for them, but they get a tough road ahead of them to make the TCAM more scalable in terms of power and performance. Yeah.
With an absolute agreement that your opinion here is just yours, not Juniper's, do you see that being more likely a future? Or what do you see maybe as the gut feeling? What's going to be the most reasonable arrangement in your mind?
Yeah, we work with the TCAM vendor too. I don't want to alienate them too much. So I think the pure TCAM approach is probably difficult to scale, but there are different ways to solve the problem using some algorithmic stuff and some of the TCAMs. So that might be a way to do that, but it's difficult. The TCAM market is, and also right now the number of vendors serving that market is decreasing pretty fast as well. So that's another factor that may or may not be technology related. It's just the price of that. I don't know how that will go in the future.
Thank you.
Yeah.
Lorenzo Coliti, Google. Thanks for the talk. It's very interesting. I don't know anything about hardware design, and it was good to see part of how the sausage is made, so to speak. One curiosity I have is that you talked a lot about the detail of the design process and manufacturing process, but what I don't know, and maybe others people do know, is How do you go from there to something that can do firewall filters and tries and things like that, which are like the upper level things? So what kind of primitives do these chips offer? Do they have an instruction set that's comparable to like 8086, or do they? What is it that they then offer to the software?
That's a very good question. That's something, I did not address. It depends on each generation. And of course, the memory choices are depending on your algorithm, lookup algorithm as well, the ACL algorithm, definitely. And some of them, I know some of the vendors use TCAM to look up because, it's kind of very natural to look up an IP address from the TCAM. And Juniper use a tree type lookup, right? So I can see in the future people will use hashing to do that as well. And I don't, there may be already implementation using that. Of course, it's very important, and the algorithm will decide what kind of memory subsystem, or even some of the lookup might be internal and some of them may be external, and that will play a big role in there. That is done in the architectural phase of the chip, of the design
So in a
phase.
sense, it's more like hardware acceleration found in graphics cards than like a general purpose CPU, right? You start with the algorithm and then you find out how to accelerate it and you tightly integrate things.
Correct. Basically, I wouldn't say start from where. It's kind of interaction. You have to consider both when you're designing the algorithm and the chips. So you have to know the technology that's available to you, and also the technology, the lookup technology, that's the algorithm technology that's available to you, and use it to your best ability at that time. And these are changing as well, as we can say, as we can see. So in a few years, the perfect algorithm a few years ago may or may not be applicable a few years from now, right? Because the technology changed in such a dramatic pace.
Thank you.
Yes.
Hi, Chris Woodfield, Yahoo. I was wondering, at what point do you tend to find operations that are easily accelerated by ASICs versus algorithms, versus operations that are better suited by general purpose? I'm wondering has that changed significantly over the years? Are there operations that used to be easier, better, more efficient to do on a general purpose CPU that are now ASICable, or has the opposite taken place?
Well, with improvement in silicon technologies, as always, everything is easier. But then also your demand on the bandwidth also is increased in exponential fashion. It's always a trade-off that you need to make during the architectural phase or the design phase. So what should be done in software and what should be done in hardware, and that there's no general answer to that. It has to be looked at in case-by-case basis. Does that answer your question?
Yeah. I think so. Thanks.
I think we need to cut off the line here. If you're not in line now, please don't get in line.
I'm Jeff Sachs. Sorry. Jeff Sachs from Blue Ridge Internet Networks.
Hi.
Thank you very much for describing all of this. I'm curious about the part of the process where you're simulating the chips before you've actually constructed them in silicon, and you're trying to simulate waveforms and timing and interactions between different chips and different parts of the chip. At what speed can you simulate that? I mean, how close is it? 1,000th of real time, 1/1,000,000th of real time, or what? How does the simulator, which is just making believe that there's silicon there, how close does it get to the real silicon, and what speed can you do it?
There are even simulation technology. There are several, and the one that I try to describe are just software simulations. It's just run on real machines. Those are very, very, very slow. It's not thousands. It's probably millions times slower than the real silicon. But there are some technology that are called emulation. They actually try to compile your chips into hardware and run it, and those will be faster. So still, but yeah, nothing compared with the real thing. With software-based approach, it's millions times slower, and then in In the emulation, probably 1,000 times slower. But the emulation, it takes more effort to put them in the emulator. So there's a trade-off there that need to be made. Yeah.
Scott White, Google. So I think I just heard you say because networking changes, the ASIC technology we buy today will not be useful in 3 years or 5 years. Is that in fact what you said?
I don't believe that, but I'm just saying, in terms of technology, I don't think the overall network protocol and all that is going to change, but how we implement that inside our ASICs may have to change.
So you're saying that the way we design networks is in fact static and doesn't change, and then the only thing that changes is the implementation of the networking?
Yeah, that I'm not sure. But
because I would in fact claim that networking changes all the time, right? And you're right that the technology changes all the time, but if you're making if you're trying to bound this and say that I have to use this hardware at this point in time because this is how the networking goes, then that really constrains the way I can build a network. And in that case, it may very well be that all this complexity that you've built into this system that nobody in this room uses 100% of all the time is in fact the wrong way to go. And your point earlier about functional layouts and compartmentalizing is well taken. But in the end, if nobody in the room wants that,
can I speak? All of these devices are remarkably programmable. So we try to anticipate the changes. So in fact, if you look at the Juniper's product we released in 1998, they are still in the networks today. And then these are remarkably programmable devices. They can adapt to changes, but of course, we have to anticipate much of this to do that. But they are very programmable devices. They have a long life. Can cope with the changes in protocols over the last 15,
so I can use an
20
IP2
years.
in place of Trio for today's technology?
You can use it. Of course, it will not run as fast, and some of the feature may or may not be supported. But yeah, in most cases, actually, you have it. The IP2 systems are still in use today.
I understand that, but if the features I want, so let me put it this way: if I don't need all the features that are in a Trio or any ASIC, if I don't need the features that are in an ASIC, yet I have to pay for that complexity today, and I never use those features, then that's a lost cost. And on top of that, you're constraining the way that I can actually design my networks. So in the end, I would suggest that ASICs might not be the right technology for the problems that your customers have.
Well, if microprocessor can fit your needs in building these gigabit routers, 100 gigabit routers, be my guest. But that's the reality here, is that they are just fall short in one way or another in terms of cost and power or features. Well, features may not be, but they cannot deliver the performance that you require at that speed.
Joel Yegley. Quick observation, I guess, partially in response to the previous question, but I think it's pretty fortunate that IP forwarding is done in the thin part of the hourglass, and that the actual feature set that we require there, from the vantage point of forwarding a packet, is pretty small. To the extent that we don't crap that up with additional complexity, I think that's a smooth move on our part. Thank you.
Okay. So
thank you very much. That was